Yeah, so the collection of papers I have that I collected was mainly around bringing some sort of structure to RL, some sort of abstractions, which help mostly in a long horizon kind of task. So the first paper we have, learning graph structures with a finite state automata layer. So this is not exactly RL, but it uh, they use RL in the the methodology uses RL, and it's some of the concepts like we can draw some pretty close parallels. So graph neural networks have become really popular recently, and they've been shown to have some really cool results. But the issue still remains that the graph has to be, like most of the time, it has to be provided. So it's usually the graph is part of a data set, or it's inferred from some human interventions, or you generally don't have the graph beforehand. I mean, yeah, you generally have the graph beforehand, but so the running example that this paper works with, and they do their experimentation on, is static analysis of Python code. So generally, in that you parse the Python code as an abstract syntax tree, and then you can do like you can compilers and stuff. I mean, it's not just restricted to Python, but any code could be passed by an AST, and then compilers can do optimizations and stuff over that. But here, what they'll be doing is, another approach to derive something from that AST is to run a GNN on top. So some empirical evidence has shown that adding extra edges where it's semantically important can have a lot of improvements in certain static analysis tasks. So yeah, what this paper proposes is a GNN kind of, not exactly a GNN layer, but a sort of intermediate neural network based layer, which adds extra edges to the graph to improve performance in downstream tasks. So the two tasks they've considered in the paper are, I'll just scroll down here, are static analysis of Python code and also navigation in a grid world. So yeah, first the important concept they talk about is L paths. So in a graph, an L path is defined between two nodes of the graph. If there is a path between those two nodes, such that that path is accepted by some finite state automata. So if you have some finite state automata, then there is a formal language corresponding to each FSA. Now, on L path, so if you have a graph, then you can extract words from those graphs corresponding to paths between two nodes. And each character of in the word would correspond to node, edge, node, edge, node, edge, node, edge, and so on. Now, if those can be accepted by some finite state automata, then that's called an L path. Now, according to what the FSA, like how the FSA is designed, collections of L paths can correspond to different things. So these are a few examples. So last read, last write, next control flow. So basically, if you have a AST and you define a certain FSA, then you can create collections of L paths such that they correspond to paths within the AST that correspond to the last read relation. So, for example, if the initial node is some variable use, the usage of some variable or the assignment of some variable, then some FSA would correspond to all the paths originating from that node and going to the node corresponding to where that variable was previously used. So that would be the last read L collection of L paths. Similarly, you can have last write, next control flow. So if you have a while loop, then you can have paths going from the beginning of the while loop to the end, encompassing the whole control flow. Or also an if else, I think if else statements also that works. So Yeah, basically these L paths defined by finite state automata can correspond to some collection of semantic relations within the program's AST. Now, this is a quote from the paper which kind of summarizes the whole approach. So the existence of L path summarizes the presence of longer chains of relations with a single pairwise relation. So generally in an AST, if we take the simple example of the last read relation, where we want to find all the places where that variable was last read. Now, that can be somewhere else in the graph, which is really far away. Now, if you use a regular GNN on top of it, uh, most GNNs generally have some sort of pooling and adding over multiple like times, that kind of setup, and that can capture relations. Uh, can capture relations, but the capturing of relations kind of decreases the farther away the farther away the two nodes that you're talking about are. Now, in this case, if you have two very nodes that are really far away, but still semantically very strongly linked because they're using the same variable, it would be great if you could link them directly, if the graph could link them directly. And generally, when this is done by humans or this is done before it's passed, the graphs are passed to a GNN, this really improves static code analysis tasks. So that's what they're doing. The layer, what they're doing is they're trying to find these L paths which summarize some semantically useful relation or nodes which should be semantically linked. And yeah, they're trying to connect them. Now, the issue is that we may not always know which language L would be useful for the task of interest. So like we can choose, okay, last read and last write are useful, but there can be lots of these kinds of relations. And it would be good if there's some sort of way to learn these relations directly according to the signal we're getting from the downstream task. So this approach makes it easy to jointly learn this language L and use L paths as an abstraction for the downstream task. So this language is directly learned. So how they're doing this is, yeah, so instead of defining these themselves, we have this layer in this whole setup where you given the graph, this layer outputs some extra edges to the graph. And then that new graph is then used in your downstream task. And then whatever loss you're getting can be back propagated through this layer. So the layer they're defining is fully differentiable. And it can be back propagated through the layer. And then the layer improves in its behavior towards adding new edges. And then, yeah, that way it can which of these L paths are the most semantically important for the downstream task. So yeah, the general setup they're using is they're putting a RL agent on the graph from some node and using it to find the important L paths. So the setup is graphs is rewardless partially observable MDPs. So the rewardless part I'll come to, but observations consist of the local information local to that node. So yeah, you only get information from the node you're currently as the observation. And so it's a partially observable MDP. And the action space is like moving from the current node to, if it's an abstract syntax tree, then okay, moving from its parent to the parent, moving to the left child, moving to the right child, and so on. Plus these three actions, which are add edge and stop or backtrack. So add edge and stop basically means that you started from some original node, your agent traversed all the way to some node, and it's decided that this node is semantically important and we should add an edge from the original node to this node. And so that's basically accepting the relation and adding a long edge between those two things. Stop it's just rejecting. It's saying that okay, I've gotten into some place and it doesn't look like there's any point adding anything here. and backtrack means going back to the place it was before. So yeah, this just characterizes an agent that can move around the graph and keep adding edges. Just give me a sec. Okay. So yeah, now the point of it being rewardless is that there's no explicit reward because the agent should learn. The agent is parameterized as a learnable FSA. So by learnable FSA, it's just that along with the current observation that it has, it also gets some sort of finite memory. So in a finite state automata, you generally have a memory element which along with an input. So that memory element and the input decide what the action that the automata is going to take. So this is emulated here with an RL agent in that you have an agent which gets the current state, the node you're in, plus the plus some finite memory element which it can edit at each action, and it takes the action according to that. So this is trying to parallel an FSA, and the whole point is it might not be an FSA because obviously you can't have a strict FSA which is learnable. So you're trying to have this parameterized, so an RL agent using a neural network, which behaves in a way which in the end will emulate an FSA, so that the paths that you're getting, the L paths that you're getting, are approximately what an FSA would do. So it's trying to bias the agent towards adding edges corresponding to L paths, and not just randomly move around or move around in some other way. But we want them to be L paths specifically, because these L paths we know can capture semantic relations. So so we have this agent and it runs around in the graph, and then we compute a Monte Carlo estimate for the adjacency matrix. So basically we have all of these trajectories, and so in some places the agent has added an edge, in some places it hasn't added an edge. So from this we just average out all of the places where the edge was added to get an adjacency matrix. And this basically, the point of this is just to summarize the paths that the agent tends to accept. And so the edges we're adding to the graph are sort of soft edges with some sort of probability attached to them. And this edge matrix is computed as this probability of action and the current. So this what this is saying is the probability that this is adjacency is just giving the probability of so this in the end would be a complete adjacency matrix of the graph where each entry indicates the probability of an extra edge being added by the agent. So I think they've given the proof in the appendix. I won't go over that here for this exact relation. And then they compute this is the probability, and then they compute the adjacency matrix by performing a sigmoid they perform a linear layer over the sigmoid and a sigmoid. So basically the point is that the agent ran around in the graph and it added extra edges, and then once these extra edges go to the downstream task, there'll be some loss from the downstream task, and that loss can be backpropagated because this is purely like all of this is completely differentiable, these operations, and you can update the agent's weights through backpropagation, and that's why the MDP isn't like it's a rewardless MDP. So the agent is getting updated according to the downstream task. So they performed a few experiments. So for example, I won't go through the complete experiments here, but like some examples you can see is the last thread. This is how the last thread relation works. So here we want to find the last thread relation for y, and you can see it was last thread here, here, and here. So what the agent does is it goes back all the way up the abstract syntax tree, and it assigns probability to the backwards flow. So remember that L paths are paths going between nodes of the abstract syntax tree. So this is what an L path would look like in the program, going all the way back to say this y, and going to this y, and here the width of the line is indicating the probability mass from this associated to each of these nodes, and the probability of adding an extra edge to these places. So you can see that the agent kind of clearly captured the semantic relation that they require of the last thread task. And here also they performed a similar thing for the grid world, where it was a navigation task from one place to another. And the point that I wanted to make by including this paper was in hierarchical RL and these kinds of methods, we often talk about options and temporally abstracted relations between between tasks, that things that we need to do. So here we're kind of doing the same thing, except say on code or on static maps such as the grid world. But by having this agent play around in this world, we're kind of creating long-term semantic. We're kind of finding long-term semantic relations which are important to some objective. And here the objective can be anything, but we can train this to in RL we can train this to be some sort of a reward maximization objective also. So this I thought was a pretty interesting way of finding semantic relations in graph. So any questions about this paper? Yeah.
Oh yeah. Sorry to interrupt. My question is, you said that the edges that the agent adds will incur a loss, right? So what?
So you'll have an original graph. So for this example, it'll just be the AST corresponding to this piece of code. Now this layer, the GFSA layer that they've developed, would add these relations that you see in green. So it would add, this adjacency matrix that it outputs would basically say that there's a high chance of this being connected, high chance of this being connected, and a high chance of this being connected. So it's basically adding a soft edge between these points. Now in your downstream task, you'll probably be using the GNN to maybe classify variable misuse or do some other kind of task on the code itself. Now for that task, this last, so here they've explicitly said that they've used the last thread task to, in which each node has to be classified according to, like if it's last thread of Y, then the node where Y was last thread has to be classified as being last thread. So over there, I think you'll have for that. So that's just a graph classification task, right? Node classification.
Okay.
So you'll have a loss over there. And then that loss will be back propagated to the weights of this agent.
Oh, I see. Okay. Oh, so I'm kind of surprised that it doesn't, like, the gradients don't vanish or something. It's just because it's pretty indirect, no?
Yeah. So actually, if you look at the paper, in the paper they've the loss term just gets the loss term just gets multiplied by this term because it's like I'm not exactly sure how the math works out, but like it seems that they've gotten results. And I think it's not that indirect also, because you're directly outputting this adjacency matrix, and it's not like the agent itself is I think it's based on this transition matrix. So the transitions that are seen in the agent's trajectories, and yeah, this wherever the agent stopped. So these two things. So I guess according to these statistics, then you're finding your gradient from these, I think. So it's kind of like what we do in policy gradient, right? Except the gradient term is being replaced by the gradient of the downstream loss.
Right. Okay. Fine.
But the advantage kind of term, which is derived from the trajectories themselves, is this term here.
Okay. Okay. Fine. But I guess in the grid world, do they try to do RL on that, or is it some graph classification kind of thing?
I'm not sure exactly about that. I'll have to check.
Okay.
It's
Yeah,
I don't think it's graph classification. It's purely like navigation only, point A to point B navigation.
Okay. Okay. Sure. We'll continue discussing this after the. Thanks.
Any other questions? Okay, so the next 4 papers are mostly about long horizon tasks. So long horizon tasks are basically tasks which require the agent to complete maybe a series of subtasks, or the episodes are like more complex. It's not just about solving a single task. So for example, if you wanted to go to the airport, then you would have to like get out of your society, like call up cabs, and just complete a series of other tasks on the way. So yeah, generally in robotics, what is really popular for these kinds of tasks, and I mean not these kinds of tasks, but other popular methods for planning are model predictive control. So where you have a model which is either learned or it's known beforehand, like derived through the dynamics of the bot, and that's used to search the space of all paths to find a path which reaches the goal. Other methods, like we also can just simply try to use goal conditioned deep RL, which tries to get to the goal. Yeah, and another method can be goal condition predictors. So where you try to predict all the intermediate states that need to be passed through to from the start state to the end state to achieve the goal. So generally the issue with all of these planning methods is that they are all sequential in the sense that they generate one goal after the other goal after the other. So in MPC, it's all of these things all of these paths that you're guessing are all rollouts. Also in deep RL, we generally take one action at a time. And in at least model-free methods. So all of these suffer from an accumulation of error when you're trying to plan. If you have a model, then errors in the model can mean that you have a lot of accumulation in the error. If you have, so generally long horizon tasks, these kinds of things aren't working well, and especially just pure RL is not working well. So yeah, a couple of papers which try to tackle this. The first paper is long horizon visual planning with goal condition hierarchical predictors from Sergey Levine's lab. So the motivation is, the current methods don't scale well, and sequential planners suffer from accumulation of error. So the kind of fields that they're drawing from here are video interpolation. So I talked about predictors, right? Sequential predictors, where you try to predict one state after the other, um, conditioned on some goal. So you're in a starting state and conditioned on some goal. You try to predict all the states you need to reach in the middle. So that's similar to video interpolation in that you have multiple sparse frames and then you try to fill in the video in the middle. The issue there is video interpolation generally is deals with very short amounts of time. So the frames aren't very far apart. So it's very different from planning, where you have to plan over where each waypoint in the plan might be separated by a large temporal or spatial distance. The closest field we have is visual planning, so things like MPC. But yeah, as I talked about MPC, another issue with MPC is that if you're in a very large environment, your goal is far away and it's very complex, visually and also visually complex. So the issue can be there's a lot of different paths to try out, and it can become computationally expensive to try out all those paths until you get to one that is reaching a goal. You also have hierarchical planning, and currently, if you look at hierarchical RL, it's generally mostly at two levels of hierarchy, and and it's generally the issue is so generally the issue is it's only considering two levels of hierarchy, and you can again that's what two levels, like you'd want to generalize to a lot more, right? You would want to generalize to whatever depth of however detail you want to get in your plan, and also be able to plan over as much high level as you want. So all of these fields generally have some issues, and what this work tries to do is to basically they use hierarchical goal conditioned approach to sample trajectories that will sample trajectories and then choose the one that reaches. Okay, so the key point here is I think this diagram kind of explains it well. So you can have sequential types of predictors where you have some latent state which is modeling the observations, and you try to predict it sequentially. So you have some state and then the next state and the next state and so on. The another kind of thing is goal conditioned sequential prediction, where you know what your goal is. So each time you make a prediction of the next state, you also keep the goal in mind. And this is what this current method is trying to do, is where you recursively break down the path that you have into more fine-grained paths by predicting intermediate states between the subpaths that you have. So for example, if you initially you'll just have the initial and final state, then you'll have a state in the middle, then you'll generate a state between these two, and so on, until you get to some level of the hierarchy where you feel it's the plan is fine-grained enough. And once you have this plan in your environment, you can use some low-level controller to execute it. And so what the method does is it trains a hierarchical predictor, which predicts some intermediate state given the two parents of the state. So it's almost like an inverted tree, kind of inverted binary tree, where you have not exactly an inverted binary tree, but you have two parents which are used for each child, and then you recursively divide and conquer, and so on. Now, how do you learn this hierarchical predictor? Well, this is the architecture. Just go over it. It's a combination of a variable encoder and an LSTM. So the exact details on how they train this is given in the paper, but basically you'll have your two states that you're trying to predict an intermediate state for, and you'll encode both of them to some latent space. And the concatenation of that will be passed to another MLP, which will give you the mean and variance to sample some stochastic latent variable from. Now, along with this stochastic latent variable, you also have a deterministic latent variable, which is the hidden state of your LSTM. And both of these, along with the, obviously, along with the latent representations of the two terminal states, is used to predict the latent state of the intermediate state. And then this is decoded to get the intermediate state. And then, yeah, so the point that they've mentioned in the paper, they combine this kind of stochastic and also deterministic latent variable, is that in stochastic latent variable, you have the optimization, you have a problem with optimizing it. And with deterministic latent variable, you can fall into failure modes and not really express the full breadth of the what you require to express. So that's why they've said that they've combined these two. And I'm not exactly sure why there are these I1 and I12 mean, but basically you have this variation LSTM, and at each time step you pass in the two terminal states and you get an intermediate state. And with this, once you have this architecture, you can use it to plan. And how they plan is, so the issue with planning with this is you generally plan to minimize some kind of cost, right? So if you have MPC, then along with reaching the goal, your aim is to minimize some kind of cost for the robot to get to that point. So the issue here is, okay, you have two terminal states and you're subdividing and you're subdividing, but where does the cost play in? So yeah, so how do we minimize the cost for that? So the main issue there is that because we keep subdividing to get to our final trajectory, if we want to minimize the cost, then we have to wait till we get the final trajectory, compute the cost over that trajectory, and then according to whatever cost it is, we have to adjust the trajectory and so on. So we have to wait till we get the whole trajectory, right? So to avoid that, they've kind of come up with this iterative approach in which they train a neural network to predict the expected cost between two states. So generally the cost function would take in your entire trajectory and give you some real valued cost. Here, what they're doing is they're training a neural network according to that ground truth cost you're getting, but to train the, to predict the expected cost between two states. Now, once you have that, you can use it while you are using your divide and conquer algorithm to produce a trajectory. So here, your initial plan just consists of your initial and final state. And in your planning loop, you sample some latent. And according to that latent and your initial and final state, you're producing a number of sub-goals. So not just a single sub-goal like you're doing here. You'll have a lot of latents, and corresponding to each of the latents, you get different sub-goals. And then for each of the sub-goals, you use your cost neural network to find the cost from the initial point, initial state, to that sub-goal, plus the cost from that sub-goal to the final state. And you try to find, you find the sub-goal that minimizes this. And then the sub-goal that minimizes this is added to the trajectory. So using this iterative approach, they can minimize the cost of without having to enumerate the complete trajectory. So they do experiments on 3 different domains, basically. One is video interpolation. So, I mean, they're doing and so 2 variables. GCP tree is this one, and GCP sequential is this one, where they, instead of using divide conquer, they sequentially predict each state in the plan. So here, predicting a state basically means predicting an intermediate frame. And you can see that it performs better than, these are some of the state-of-the-art video interpolation methods that they use to compare against. Now, the more important experiments, I think, were this visual planning and control. So here they've used it on this maze world, and you can see how this works in action. So yeah, initially the state number 1 is taken as the sub goal. So this is the start state, this is the end state, and this is taken as the sub goal. These are between the start and this state and this state and the final state. So we get state number 2 and this state number 2 here. And then again, that can be divided into this, you'll get a state here also, you'll get a state here, and so on. So this recursive approach gives you a more and more fine-grained path each time. And the biggest advantage over MPC here is that you know that every path you generate, every trajectory you generate will be correct, in the sense that it will be going from start to end. Whereas in MPC, you have to guess a lot of like rollouts, and until you find one that reaches the goal. So yeah, this is how this might be done in a visual domain. And you can see the comparisons of. So visual foresight is MPC, and these are some rollouts that it tried, but it doesn't reach the goal. GCP flat is just the sequential one without the hierarchical divide conquer method. So you can see this is very like suboptimal, and it can follow some random kinds of paths. But your GCP hierarchical in this step, and it chose this one because that was minimizing the cost. Then again, it used the divide conquer. Again, it chose the. Okay, so if there is a parent node, which is say it has this tree. So yeah, it has this initial breaking point in land, just when it is the agent is about to drop the object into the bottle. So this was like a drop. So the agent had to navigate to the bottle and drop the object. And you can see that, yeah, the major turning point in the plan is happening when it's just before dropping the object. So what it's kind of saying here is the tree that you're building through this divide and conquer method is able to understand temporal abstractions over the it's able to understand temporal abstractions over the whole trajectory, over the whole environment. So yeah, I thought this was a really cool way to approach hierarchical planning. Like I think the main this kind of idea might be pretty common to recursively divide your trajectory, but I think the main innovation here was this this architecture they have that does actually work and is actually able to produce relevant states, and also the way they've handled the cost for the planning. Yeah, the next paper is sparse graphical memory for robust planning. So yeah, this is also tackling the long horizon planning problem. But previously that was hierarchical kind of planning. This is using memory for planning. So uh, unlike deep RL methods, there are a lot of classical methods still used in robotics, which are really like effective and give you concrete plans, such as like a simple one is A star search, but you also have all of these really cool probabilistic path planning algorithms also. So um, all of these is like simple classical methods based on graph search, but and they can give you plans really quickly and properly also. The issue is that they assume that there's some kind of abstraction available over all the states into a graph. So yeah, this paper tries to combine those two things, the yeah, deep RL methods with classical search. So current graphical memory, there are methods which build graphs out of experience that an agent has in the environment. So whatever states you have in the replay buffer, you can build a graph out of that. Yeah, you can build a graph out of that where the nodes are the observations themselves and the edges are the actions you took to get from one observation to another. And then you can then use some sort of A star or Dijkstra algorithm to plan over that. So issue is that in complex environments, you can imagine these graphs get really dense. Like if you're planning over if your observations are frames, then you'll be getting like thousands of frames, and your graphs will be like tens of thousands of nodes big. And yeah, these dense graphs are really hard to plan over. And the more dense your graph is, the more chances that there are that the graph is incorrect. So the biggest issue you can have in your graph is that there exists some edge which maybe goes through a wall or traverses some untraversable area, uh, or a node where it shouldn't be. So all of these places, these things can happen as errors creep in with as you get more and more nodes. So the sparser your graph, the better. And yeah, some methods use human intervention to generate like graphs which are robust. But what this method does is it learns it builds the graph on its own. And the key thing is it keeps it sparse. So while it's building the graph is kept sparse and clean also of any unnecessary edges. So that, yeah, you have a graph which is easy to plan over, and it doesn't have any. They also talk about a cleaning procedure so that the graph doesn't have any incorrect edges. So how do they do this? Well, the policy is composed of two policies: a high-level policy, a low-level policy. So the high-level policy is conditioned on the goal, and the low-level policy is conditioned on a waypoint given by the high-level policy. So a simple two-level hierarchy. Your high-level policy is over the graph that you've built from your experience, and that can be Dijkstra's algorithm, it can be A star, any graph-based algorithm. And once you get a plan through your graph, you can use any low-level policy. So in this work, they used distributional DDPG. So and they trained this. I think they trained it in different ways for different environments. For one environment, they used behavior cloning. For another environment, they trained it they trained it using regular RL. So you can train it however you like. So these two policies are basically independent. And the low-level policy will get the waypoint from the high-level policy, and it will try to go towards it. Sorry about that. Yeah. Okay. So how do you construct this memory? So this is the most important part of the paper. So quote is sparse graphical memory is constructed from a buffer exploration trajectories by retaining the minimal set of states that fail the two-way consistency criterion. So instead of having all the states in the graph, a lot of them will just be redundant, right? So you try to tease out all the states that are redundant and combine them into one. And they use a two-way consistency criterion for this. Two states are equivalent if they are interchangeable as both goals and starting states. So the issue, I mean, the most obvious thing might be just to take like the L2 distance or something between the two observations. The issue with this is two states might be really similar, but they are not interchangeable in that suppose you have a state where your bottle is really close to the edge and your bottle a bottle is on the edge of the table, and if you let go of the bottle it falls off. Now these two states aren't equivalent because you can't if you the state where the bottle is falling off the edge might be visually very similar to being close to the edge, but the bottle which is falling off the edge is can't be recovered, like it can't go back to that state, right? So if you merge those two states, then you'll have problems in your planning because your high-level planner might assume that that's a safe state to go to, or that state will allow us to go to some other place, but whereas in fact it's just just lets you fall off the table. So that's why L2 distance are visual similarity metrics are an issue. So they think about some temporally similar observations. So like perceptually similar observations look very similar, but there can be issues there. So they try to go with temporally similar observations, and they use the two-way criterion, consistency criterion. And you can see here, so state S1 and S2 are equivalent because they're interchangeable both as goals and starting state. So you consider all the neighbors around these two states, and you consider both of them as you take S1 as the starting state, and you see if there's a path from that state to this state, and take S2. And suppose for one there is a path, for the other there isn't a path. That means that they aren't equivalent for your high-level planner, right? So then they'll have to be kept independent nodes in the graph. But if you find that all of the neighbors can get to them and you can go to all of the neighbors in the same amount of steps, then that means that they're equivalent and you can merge them. So you can see an example of this in real life. So they use this Wisdom environment. So this is the top level view of the environment. It's actually like a 2D POV, a POV 3D environment where you get a POV RGB image. So initially, when the agent finishes the exploration state, it has 20,100 states. And this is like too big, both in terms of computation, and you'll have a lot of errors in this also. So after this, you apply the sparsification, which, so yeah, you can imagine that you can't check pairwise distances for all nodes. That's like an NP-hard problem, which is computationally like too expensive. So then they've developed an iterative procedure where they build a set of nodes which are independent of each other according to this criterion. So they choose one initial node, and then they keep adding a node to this set if as long as the two-way consistency criteria is not satisfied. So if it is satisfied, then yeah, that means that they're equivalent. So you keep adding independent states to this set. And because it's an iterative procedure, it just scales on the order of the number of observations or nodes you're adding. So yeah, after that sparsification algorithm, you can, they went down from 20,000 to 2,000 states, but you still have a lot of edges. So you have 22,000 edges. So they apply another kind of cleanup, a simple cleanup procedure, which is they limit for each node, they limit the number of edges to some k number of edges. So they haven't mentioned how many, edges here, but like some nodes might have unnecessarily large number of edges. So you just limit it to some k, some finite number of edges. And that way they go from 22,000 to 9,000 edges. And they then use a cleanup procedure. So a cleanup procedure basically uses the agent and it samples some sub goals within the environment. And it tries to go to those sub goals using this graph that you have. Now, suppose while doing that, you encounter a wall or something while going from one waypoint to the other. That means that the edge between those two is actually incorrect. So then you remove that. So it's like basically a manual procedure where the agent has to go around checking how much of the graph is correct. So after 144,000 of these kinds of steps, cleanup steps, so this is randomly just exploring the environment to see which edges are correct and which are incorrect. You reduce the edges to sort of 7,000 and you have 2,000 nodes. So this graph is that they get can be used. I mean, you can see there are very few incorrect edges here, and it is sparse enough that you could plan like using Dijkstra's or A-star pretty easily, and get a path through this. And this was like on a video game environment. So it like one of the initial doubts I had was how feasible could this be in for continuous observation spaces, but this kind of shows that it's definitely doable. So the build sparse graph algorithm, yeah, this is the iterative algorithm that they use. So they start with an empty set. They keep adding vertices if they are novel according to that two-way consistency criterion. If it isn't novel, then you don't add it. Yeah, and you keep growing your vertex and your edge set like that. And then after that, you apply the three cleanup procedures. One is sparsifying the graph based, the two cleanup procedures. One is just limiting each node to k edges, and then cleaning up by manually letting the agent play and traverse the environment, and then removing edges which seem incorrect. So yeah, they perform experiments in three environments. A point environment, which just gives x, y coordinates as points. The x, y coordinate you're in, and it's a simple maze. So here, the 4-room maze. You have to go from one point to another. Wisdom, you get like this POV RGB image. Safety gym, you also get this POV RGB image. And you have to navigate through the environment to do certain tasks. So they compare their methods, and you can see this is for point M, this is for Wisdom, and this is safety gym. And SORB is search and replay buffer. And SPTM is also one of the older methods. So SPTM requires human interventions to build the graph, and search and replay buffer is a previous method which also uses graphs but which doesn't sparsify at all. So you can see the success rate goes from 28% to 100% for reaching the goal once you use the sparsifcation method after building the graph. Again, for SPTM, you have a massive improvement, and similarly here. And they also measured how much the cleanup steps matter. So cleanup steps in that manually letting your agent move around and check incorrect edges, and you can see that in Wisdom that it does make a difference for at least for the easy and medium environment. You get like here 10%, and again 4% improvement. So it's probably you get diminishing returns, but the cleanup steps are really important. And they also compare different methods for sparsification. So the two-way consistency thing is what they thought of, but they also thought of like different criteria on which they could use. And they find that two-way consistency is the best in that way. So and here again, they check success rate of reaching the goal with search and replay buffer. It's very low success rate. and even with larger pre-map time steps, and similarly safety gym. But in safety gym, the success rate doesn't grow as much. And when you make this graph sparse, it really makes a difference in terms of your success rate in all environments. So yeah, the sparsification graph, I guess. Okay, there's a question in chat. Oh, cool. Yeah, so sparsification makes a difference, and it makes this whole graph-based approach really viable. So I guess if more works build on this, we can start to get graphs and graph-based methods which make semantic sense. So this helps, I think, in terms of RL. Like you could think of this in terms of RL safety, constraining paths within the graph to certain areas. You can think of it in terms of explainability also. So instead of just like a black box navigation device, you can get real plans out of this. So yeah, any questions? Cool. So yeah, these two I'll just go over quickly. They're more on the neurosymbolic side. So this is neurosymbolic RL with formally verified exploration. And this is really important. I think, yeah, the main aim of the paper was safe RL. So previous approaches to safe RL usually take three approaches. One is constrained policy optimization. So you constrain the policy that you are building to only exhibit a certain behavior while you're optimizing it. Shielding is you have your regular RL policy, but you also have a fallback symbolic policy, and you keep checking if your RL policy is going out of bounds or doing something dangerous. And whenever it's doing something dangerous, you fall back to your symbolic policy. And formal verification is you constantly keep checking whether your neural networks are performing within certain bounds. So these were the previous kinds of methods, but what this method tries to do is kind of combine shielding and policy optimization, because the issue with pure shielding is that your shield doesn't change. So the shield you specify has to cover all observations that the agent might encounter. So yeah, that can be tedious for really complex environments. And constraint policy optimization doesn't provide any theoretical guarantees for safety. Whereas shielding is really safe, but yeah, it can't really adapt. So it tries to find some middle ground. For this, the setup is this augmented MDP. Most of the things are the same, except for this p hash function, which is a function which takes the states. Okay, yeah, and it defines the worst case bound. So the states, and yeah, I think this should be A. But the states and actions, and defines a worst case bound, as in for the environment at any state action pair, what are the possible safe states that the agent should be able to go to. So from this, the output of this function, this is given by the user, or by, like, this is previously defined, it's not learned. And yeah, it defines the safe areas, or safe areas for each state action pair. And SU defines the unsafe states within the environment, like the absolute unsafe states that the agent should never go to. Your policy pi is defined to be safe if all the states reachable with that policy are safe. So if the policy ever if any states is reachable under the policy which is unsafe, then the policy is unsafe. And the goal is to find a policy that is optimal with respect to it's optimal with respect to your usual RL objective, and it's also safe. So that's the objective. So the policy here, this is the interesting part. The policy here consists of three things. You have a G, which is your shield. you also have a set of safe states that you previously defined, and F, which is a neural network policy. And you choose your action according to this rule. So if the, okay, sorry, this I kind of misexplained. This p hash function gives the all possible states that an agent might reach after taking an action in a certain state. So what this is saying is, if all of the possible states that the agent might end up after taking the action defined by the neural network, then take the neural network action. But if the neural network action is leading to any unsafe states, then take the shield action. So this is, I mean, this is pretty much common sense. Like if the neural network is leading to something unsafe, take the shield. Yeah, and the shield is by symbolic policy. The shield is a collection of linear policies, linear in the state, uh, defined according to some like this, some, I guess, some first order logic condition. So these conditions partition the environment up into certain regions. And for each of those regions, you have a different linear policy. And this whole thing is the shield. So in some regions, you might want to go right, some regions, you might want to go left, and so on. And this whole thing defines that. So now this is, so once you have this, you want to basically be able to, obviously you'll be able to learn your neural network through simple policy gradient, but you also want to be able to update your shield as your neural network improves. So how do you do that? So the algorithm consists of 3 stages: a lift, update, and project. So lift is basically you train a neural network to imitate your shield. So initially you start off with some shield, some limited shield that you're given to the method. So this has to be provided like beforehand. But this doesn't cover the whole environment. And the point is that the agent will keep on updating the shield as it goes along. Now, initially you train a neural network to imitate the behavior of the shield through some imitation learning method. So yeah, any imitation learning method you can use here. I think they use Dagger for this. Then you update, yeah. So once you've done this, you use the neural network to do replays, like to act in the environment according to this action rule. And after you've got a bunch of trajectories, you use simple policy gradient to update your neural network to F dash. Now you want to update your shield. So this is the tricky part. To find the improved shield, so here you have to find a shield G dash that minimizes the distance between, the distance to the behavior of this policy G, phi, and F dash. So remember, the policy is a collection of shield, safe states, and neural network. So once you've updated your neural network, you've got an updated policy. So you want to find a shield that behaves as closely as possible to this updated policy. And this distance is given by Bregman divergence. So I think Bregman divergence is a class of distance metric. So I guess L2 distance is one of them. It can also be used to find distance between the outputs of functions. So yeah, they've done, they can go through the math in the paper exactly. But what they're doing is, since all of these are linear functions, you can, to update your G to G dash, what you do is you choose one of these GIs according to some heuristic, and then you split it up. So you got to understand that these first order logic statements are dividing the environment up into regions. So then you can choose some heuristic to choose one of these regions and then divide the region up. And then for both of those, you have a different, say, G1 and G2. Now, those G1 and G2 that you have will be, since these are linear functions, they will be like parameterized to solve an optimization problem, a constraint optimization problem that minimizes this D. So this distance to the behavior of the updated neural network. So basically what you've done is you've split up a region in one of these and then updated the shields of those regions to match the behavior of the neural network. So over time, you'll be update, and the way they're doing is since this is a linear policy, you just you solve a constraint, a constraint optimization problem to minimize this distance. So that way you have an updated shield which performs better. Yeah, which matches this more closely. So yeah, once you do this iteratively, what you'll be doing is improving your neural network policy and also updating your shield along with it. And they show that there is a regret bound theoretically. And so this is the expected regret and this is the optimal regret. And this is bounded. So these terms you can ignore. It's importantly, it's bounded by this hyperparameter that you choose, the probability that the shield is invoked. So not a hyperparameter, sorry, but the probability that the shield is invoked. So the more times that the shield is invoked, the higher your regret will be. In a linear way. So we have to minimize this this probability of the shield being invoked, and this can be done by having your neural networks be as safe as possible, and also your shield being as adaptable as possible. So the point is that their method kind of tries to minimize this regret bound. Now, they performed experiments and compared against like unconstrained DDPG, Revel, which is their method, CPU constraint policy optimization, and static, which is a pure shielding method. So you can see that, I mean, Revel is the blue line, so it does much better than CPU overall. And one of the issues was, like one observation they had was the shield takes much, like in the running time, the proportion of the running time devoted to updating the shield is much more. So you can see in some places it's as high as 95%. So that's because you have to solve this constraint optimization problem. So I guess there's some work to be done there, but since it's a symbolic method, I guess the optimization methods will definitely take time. And yeah, this is the most important, I think, result was the trajectories for, so they have to go and reach this green path by avoiding this red. And DDPG straight up, like it learns to avoid the red, but it's not safe because even after many iterations, it still processes the red a bit. Now your CPU, constraint policy optimization, and Revel perform like pretty much similarly here. And the static shielding policy, you can see that there is a clear part where you can see that the shield is kicked in. So here, the neural network policy is probably wandering around. And when it starts to get too close to the red zone, the shield kicks in the linear policy and pushes it away. Similarly here, this is a simulated cruise control system. And the x-axis is, I think, distance from the next car, and the y-axis is, I think, acceleration. So the DDPG and CPU are straight up unsafe. So they go and crash into the next car, whereas the static and the Revel policy is safe. So yeah, basically they're trying to say that it's both safe and kind of optimal in its behavior. So yeah, this is a neurosymbolic approach which try to do this. And I'll quickly go over the last one, which is Boolean task algebra for RL. So